it or?
Yes, sure. Yeah,
Okay,
Let me just turn my phone off.
Oh, hello everyone out there. This is the International Space Science Institute Game Changer Seminar Series again, where we look at missions that changed the game in the space sciences. I am Tilman Spohn, and I'm your host here, sitting in ASI, at the ASI in Bern, Switzerland. Today, we continue our seminar series with a talk on Cassini-Huygens at Titan by Athena Coustenis, and next week we'll have Jessica Agarwal talk on Rosetta. Now, if you missed any of the previous talks, you go to our website and you can view those talks because we record all the talks and have them on our website. If you want to stay a priest of the seminar and other ISI activities, consider subscribing to our newsletter. If you go to our website, right to the bottom, there is a way to subscribe to the newsletter, and then you will get all the announcements of future seminars and so forth. It's my pleasure to introduce Professor Athena Coustenis as our today's speaker. She has roots in Greece, as you see from her background screen, I think. But for many, many years, she's been at the Paris Meudon Observatory. She is the director of the LIGA there, the Laboratoire des Études Spatiales et de l'Instrumentation en Astrophysique. I hope I didn't ruin that too much. And she's involved in many NASA and ESA space missions and has served on a large number of advisory and managing committees for the agencies ESA, NASA, for COSPA, the AAU, ISI, IUGG, EGU, and so forth and so forth. She's the chair of the Space Science Committee of the European Science Foundation and a highly cited and respected expert for planets and moons of the outer solar system. Athena, the floor is yours.
Hi, can you hear me?
I can hear you, yes.
Yes, can you see my screen?
No,
we cannot. No.
Okay, all right. So we are back.
Actually, I think we lost you.
So do you see it now?
Yeah.
Okay. Yeah, but I can't move. All right, we seem to have a small issue here. I am going to reboot. I'm very sorry, everybody. This is the joys of of these presentations. I'll be back.
Okay, folks, while Athena reboots her computer, I'll just take over the screen and show you where to subscribe to the to our newsletter. And well, I thought I could. No, oh, this is really something today.
I really don't know why, but okay. Sorry about that.
Oh, here is the place where you can subscribe to the newsletter. Now, Athena, if you're back with your presentation, just take over and share your screen with us.
Do you see my screen? Do you hear me?
We hear you, yes, but we don't see a screen.
Okay.
I stopped sharing my screen. Now you have to share your screen.
Okay. All right. Apologies. Let me see if this is going to work.
Yeah, now we have it.
Oh, no, it still doesn't want to move forward. Okay. All right. This is a bit weird because
you can click with your mouse on the screen and it advances by that. Yeah.
All right. Tillman,
but we don't see you, Athena. We don't see you.
That's okay. I think if you don't see me, that's fine. I'll turn on my screen at the end. I don't want to touch anything else at this point. Okay. Because we have a lot of ground to cover. This is a talk about the Cassini-Huygens mission on Titan. And as you know, this wonderful mission did wonderful things in the Saturnian system. So we have a lot of ground to cover. So I am going to focus today on the science achievements with respect to what we knew about Titan before Cassini got there. So please, I want to refer you all to an excellent talk on the Huygens probe mission and lessons learned by Ralph Lorenz. It was one of the International Planetary Probe workshop seminars, and that was on the 30th of May. And Ralph explained everything about the mission. I'm going to just refer to what we achieved at Titan with Cassini-Huygens. And let me start with the Voyager missions. The Voyager missions, which were just absolutely fantastic missions, wonderful machines, which had provided all the images actually that we had before the beginning of the 21st century. And I myself worked on the Voyager iris data of Titan. So the Voyager spacecraft, as you all know, the Voyager 1 at least, launched in '77 and arrived in the Saturnian system, made its closest approach of Titan on November 12, 1980, at a distance of only something like 6,000 or 7,000 kilometers at the time to the satellite center. And Voyager 2 flew by Titan also 9 months later, but at a distance 100 times greater. So these were absolutely fantastic missions that showed us Saturn's satellites as we could see them on this view graph here, where you see that among all the satellites that look like dead, inactive bodies, Titan is different. Titan's visible appearance at the time was quite unexciting, like an orange ball covered. This was the result of it being covered by a thick haze and allowed no visibility of the surface. But what makes it really important and really unique is its atmosphere, obviously. Now, before that, we knew a few things about Titan. Let me tell you some of its history. What you see up here on the right upper corner is Christianus Huygens, who discovered Titan in 1655. And after that, it took a long time before we got news from Titan. And the news came by Catalan astronomer José Comas y Solà, who claimed in 1908 to have observed limb darkening on Titan. Methane bands were first detected and other hydrocarbons in around 1944, essentially by Gerhard Kuiper of Chicago University. So Titan's more discoveries came from the Voyager mission, so where we found out what was the orbital period, about 16 days, discovered the main component, which is dinitrogen, very much like what we have in the air of the Earth. And we also found out about the mass, the radius, which is about 2,575, half of that of the Earth's. We got the mean density, the gravity, and the mean surface temperature of about 93.5 K. And an atmospheric pressure very close to that of the Earth's at 1.5 degrees, 1.5 bars, sorry. But what was important also was that we also had ground-based and earthbound observatories observing Titan. And we got a lot out of those ground-based measurements. But what we admired when Voyager came near Titan was obviously the atmosphere. It was observed to be having a detached haze and a structure very similar to the Earth's, which exhibits the features that characterize also the Earth's thermal structure. That is the atmospheric layers that include a thermosphere, a mesosphere, a stratosphere, and a troposphere further down touching the surface, with two major temperature inversions at 40 and 250 kilometers. And that corresponds to what we call the tropopause and the stratopause. There's also a mesopause further up in the atmosphere. The temperatures that are associated with this structure and the inversions in particular are about 70 degrees at the tropopause, and that's the smallest temperature we have recorded on Titan. And we have 186 K maximum respectively in what we call the neutral atmosphere. So we found a lot from Voyager. Like I said, essentially the atmosphere's main composition and the chemistry in there. And so we know that nitrogen is the major gas, and we also have second and third, actually methane and hydrogen. Methane is about 1.5 to 5% in the atmosphere. And these two molecules combine and photodissociate in the upper atmosphere and recombine to create other molecules and products, like for instance, the hydrocarbons and nitriles that we find in the atmosphere. Very little oxygen was discovered, and that was actually something that we found with the ISO observatory, the Infrared Space Observatory, and we found a little bit of water vapor and CO and CO2 in the atmosphere. Now, 90% of the energy at the surface of Titan is held by a greenhouse effect due to the nitrogen, methane, and hydrogen that exist there. Symmetrical molecules, which normally do not have a greenhouse effect on Earth, but they do on Titan due to the dense atmosphere. So we found out that there is a methanological cycle that is very much the same as the hydrological cycle on the Earth, except that it's essentially based on methane. And you can see on this diagram here how this methanological cycle operates, with the methane evaporating from the surface, getting into the atmosphere, photodissociating, falling again down towards the surface, creating condensation, clouds, and possibly methane rain. But we still didn't know from Voyager anything about the surface, its composition or structure, or the interior. We did find, though, out, as I said, a lot about the atmosphere, and it was my thesis, my PhD thesis subject, to work on the Voyager infrared data that we had at the time, which came out of only one flyby that Voyager 1 made of Titan in 1980. And you can see here that from the scarce spectra we got at the time, we managed to get the composition at the equator, also sometimes further up in latitude, and we got the vertical distributions of all the absorbing trace gas species that we had in the atmosphere. And this is a paper in 1989 that we published. So Titan, it became very obvious that it was an object of interest, because everybody thought it provided a really good analog, like a laboratory, to study some of the processes that affected the primordial Earth because of its resemblance in the atmosphere, which could have been similar to the Earth's primordial atmosphere. And like I said, the methane cycle is something that we didn't find anywhere else. The dense atmosphere is something that we didn't have anywhere else. And with all of these processes creating haze, precipitation, and deposition on the surface, the question was, how would all of these combine and what we could find actually in Titan? In terms of the surface, Lunin et al. In 1983 had suggested that this amount of ethane that we found as a byproduct could resolve the paradox of the low near surface humidity that was recorded by the need of a surface reservoir of methane, also because the methane should have been depleted in only a few decades of million years. And so we, at the time, not knowing very much, Jonathan had suggested that it was probably a global ocean covering of hydrocarbon liquid covering Titan's surface. And later on, he actually, in anticipation of Cassini-Huygens observations, he revised this model, and various landforms and surface processes on Titan were considered theoretically with varying degrees of success. But this is from Lunin 1990, who actually depicted the schematic of the system, which is excitingly close to what was finally observed. So kudos for excellent foresight there. Also, like I said, in the time before Cassini, we had some ground-based observations. These are observations performed by Smith, Lemon et al. And published in 1996 with a Hubble Space Telescope, which indicated that indeed there was no reason to think that there was a global ocean on Titan's surface, but rather an inhomogeneous surface with possibly areas, elevated areas that could be actually craters or liquid extents, but in any case, not homogeneous. And this was confirmed in observations we made with a very large telescope in Chile with adaptive optics in early 2000 in anticipation of Cassini's arrival. And we saw there that we had this surface that showed bright and dark regions. At the time, all we could say was that there are bright and dark regions. And the X you see in the middle is where actually Huygens landed, a very interesting intermediate region near the equator between the bright zones and the dark areas. So we also had a great anticipation for this unique world, knowing that the orbital inclination of Saturn, that Titan follows obviously around the sun, is about 27 degrees, very similar to that of the Earth. So that on Titan, we also have seasons, albeit they last about 7.5 years each, since Saturn takes 30 years to complete a revolution around the sun. And so this was very interesting because obviously we wanted to see what an object that has seasons, but so much longer in time looks like. And the Earth day on Titan is 16, one day on Titan is 16 days, 16 Earth days. And that was also very important and very intriguing, in particular for people who think that 24 hours are not enough to do what they have to do in a day. So all of this led us to develop a mission called the Cassini-Huygens mission, which was quite an achievement in strong international collaboration. But before that, I wanted to say that in particular for myself and for my colleagues, Paris has a special interest in that mission because Cassini, one of the two people after who the mission is named, observed Saturn in as early as 1684, Paris Observatory, and found a number of things, among others, some of the satellites and in the rings around Saturn. And this is depicted here, where you see one of his writings saying, I saw 4 different satellites around Saturn. So very strong interest from the observatory because of Cassini's achievements in the area of the Saturnian system. Obviously, what he did for the Saturnian rings is immense because he was the one who discovered the Cassini division. But also Christiaan Huygens, who was actually an amateur astronomer, discovered Titan, as I said before, in 1655. And here you have a book showing his observations and Cassini's observations at the same time. So it was very fitting that this mission would be called Cassini-Huygens. And here is the spacecraft, which was actually one of the largest and heaviest and more complex interplanetary spacecraft ever built. And only the 2 Phobos spacecraft sent to Mars by the former Soviet Union were heavier. And was loaded, obviously, with an array of powerful instruments and cameras. It was capable of taking very accurate measurements and detailed images in a variety of trajectory conditions. The 2 elements that comprise the spacecraft is the Cassini orbiter and the Huygens probe. And so Cassini has unique features. One of them is it was the first planetary spacecraft to use solid state recorders without moving parts instead of an old tape recorder. And it communicated with the Earth through its antenna subsystem consisting of 1 high gain antenna and 2 low gain antennas. The primary function of the high gain antenna was to support obviously communication with the Earth, but it was also used for scientific experiments. So during the early portion of the long journey to Saturn, the high gain antenna was positioned toward the sun, functioning like an umbrella to shield the spacecraft's instruments from harmful rays of the sun. And this is important because you'll see at the end of the mission, this antenna kept looking at the Earth as much as it could to deliver the data we have today. There was a whole set of Cassini science objectives that were put together by the scientists, obviously, who wanted to do a lot of things concerning the system's magnetosphere. Saturn also find out a lot about its properties, its rings. I'll let you read all of this. Very ambitious mission. Also for the icy satellites to look at the geological histories and characteristics, the surface composition. And for Titan, it was very important to cover a lot of the science objectives that we couldn't do from the ground or from space observatories regarding the atmosphere and the surface. So this is the Cassini-Huygens spacecraft again, with its 12 instruments on the orbiter and 6 instruments on the probe. The human functions on the right, I always like to show, because for us, it was really, for us who followed the mission from the beginning, was like our baby, but the real baby was if you can look at the picture, it was the Huygens probe that was carried by the Cassini spacecraft, which was equipped for 27 diverse science investigations. It had all kinds of instruments. It had the remote sensing palette with instruments that studied Saturn and its rings and moons in the electromagnetic spectrum. We also we had cameras, we had instruments to look at the dust, the plasma, and magnetic fields around Saturn. We also had instruments for radio waves and radar. So with all of these instruments on board, the objectives that we had for Titan became, as I said before, very detailed and very ambitious. You can see here the specific objectives that we charged the spacecraft and the probe with to look at the abundance of the atmosphere's constituents. Isotopic ratios were very important. Look at vertical and horizontal distributions of trace gases, measure the winds and global temperatures, determine the physical state, topography, and composition of the surface, and investigate, very importantly, the upper atmosphere. So basically, I want to show you in a couple more slides to say how big the team was behind the Cassini-Huygens mission. What you see here is the Cassini Saturn Orbiter science team, and you have in here the PIs of the different instruments, some of the interdisciplinary scientists. You also have the project managers and the project scientists. At the time, it was Jean-Pierre Le Breton for the probe, and Nicolas Altobelli has taken over since. And it was Dennis Matson for Cassini, who was the NASA project scientist, and Linda Spilker has taken over from him at the time that we're talking of at the later stages of the mission. So there were a lot of people behind this mission, and you can see a picture here that was taken in June 2017 with mission members at the JPL, and you can see the crowd here and all of them cheering for the Cassini mission. The Huygens probe was also another element that was very important. It consisted of the probe itself, which descended to Titan, and the probe support equipment, which remained attached to the spacecraft, which included the electronics that track the probe, recover the data that were gathered during its descent, and processed and deliver the data to the orbiter that transmitted to the Earth. And 3 parachutes were used to attenuate the speed of landing, where the probe was expected to survive for only 3 minutes. So here is the Huygens probe experimenters. I know John is connected online. He'll recognize the fabulous team of the 6 PIs behind the Huygens probe, and Jean-Pierre Le Breton, who led the whole project to the success that we know of today. There were experimenters because we really didn't know what we were going to find inside Titan at the time. So these people were real pioneers, and they came from different countries. You can see here the different country distribution for the Huygens payload with the different possibilities that the instruments could do. And each one was designed to devote specific measurements, to acquire specific measurements for different aspects of the atmosphere, and possibly something on the ground if we landed and didn't crash. So the Huygens probe was actually designed as a descent probe and not a lander, because we didn't know what we would land upon. So I want to insist on that, because this is how this probe was designed from the beginning. One of the instruments on board was ASI, the Huygens Atmosphere Structure Instrument. And here is a photo from 1991 in Canterbury, in England, where the ASI team at the time was gathered together. You can see Marcello Fulcignoni and John sitting up there in the front. Several other people, Ralph Lorenz is to the right, several other people are there, Arimati Hari, Hakan Svendhem, and others. And you can see this strange person in the middle of the strange hair and the glasses. That was me at the time. I was really very young. But this was a fantastic team again, and we stood behind this special mission that left from Cape Canaveral and went all the way to Titan, flying, using gravity assist, obviously, to travel through about 3 billion kilometers in something like 7 years and take us to a strange new world. The launch, we were, some of us, very lucky to attend on the 15th of October, 1997, something close to 5 a.m. It was a fabulous launch, really wonderful one from Cape Canaveral, and we were all very happy and very emotional at the time. And you can see the picture here with a maquette of the Huygens probe. And the mission, after this perfect launch, took us through the solar system with several flybys. One of them is shown here for Venus. There were actually 2 of them. We went by the Earth. We also crossed an asteroid called Mazursky, and we arrived in the vicinity of Jupiter end of the year 2000, where the Galileo mission was still there and operating, and we made some fabulous measurements with the 2 missions of the magnetosphere of Jupiter. And then we approached Saturn. This is one of the first images we got of Saturn in 2002. And the mission was supposed to last until 2008, but it was extended for another 2 years until September 2010. That was branded the Cassini Equinox mission, and it's extended a second and final time with the Cassini Solstice mission, lasting another 7 years until September 2017, which we'll talk about later. But on the 1st of July 2004, the mission arrived around Saturn, and after some very frightening ring crossings, Cassini got into orbit around Saturn. And the amazing discoveries started. In particular, I don't have time to say everything we found out about Saturn and the magnetosphere and other things. I want to focus on the icy satellite science highlights. And one of the highlights, obviously, was the tiny moon Enceladus, which is only 500 kilometers in diameter, a puzzling moon with dramatic jets of organic lead and water vapor and dust-sized icy particles emanating from its south polar region. And this is possibly coming from liquid water reservoirs under the surface. The plumes are composed of salt water laced with grains of silica-rich sand, nitrogen in ammonia form. It's got nutrients and organic molecules, including trace amounts of simple hydrocarbons such as methane, propane, acetylene, and formaldehyde, which are carbon-bearing molecules. So this indicates that there is hydrothermal activity, which is an energy source at work in Enceladus subsurface ocean. And in addition, models indicate that the large rocky core is porous, allowing water to flow through it to pick up heat. So Enceladus, we know now, is also the main source of the particles for the E-ring, which was confirmed by Cassini's first 2 close fly-bys in 2005. And so we know that Enceladus is really now one of the divas in the Saturnian system. But other moons like Mima and Dione may have also oceans beneath their icy crusts. There was the mystery of the dual bright dark surface of Enceladus. So Cassini really turned our understanding of these icy bodies around, because now we know that they are not dead inactive bodies, but very much active, in particular underneath their surfaces. But of course, besides Enceladus, the other very important moon in the Saturnian system was Titan, that we discovered at the time to possess features we had never imagined in our wildest dreams, I would say. So let me focus now and come to Titan by Cassini-Huygens. And here are some of the science highlights we got. Obviously, the Huygens probe made a first landing on a moon in the outer solar system. This is the furthest ever human-made machine that human-made machine has ever landed. And it's also the first time we've landed on a satellite. There was the discovery of a lot of prebiotic chemistry on Titan before with Voyager, but now we know a lot more about where it comes and what is the degree of complexity we can expect. There was the discovery of meteorology, seasonal effects, and different processes throughout the atmosphere, but also the discovery of a dense, salty global ocean of liquid water below the thick icy crust of the moon. So I'm going to go through a little bit more detail on all of these aspects. So Titan's atmosphere is very complex. It's an organic factory. But a big leap that we got in our understanding of Titan's chemical structure came from Cassini, and in particular the measurements by the ion and neutral mass spectrometer, INMS, in the ionosphere. Titan was found to have a quite extended ionosphere, and this is due to the lack of a strong intrinsic global magnetic field. But the high energy photons and energetic particles from Saturn's magnetosphere are main energy sources in Titan's upper atmosphere, and they create an extended ionosphere that goes between 700 and 2,700 kilometers. So as Cassini flew through the upper parts of the ionosphere, it discovered a multitude of complex positive and negative ions, with masses reaching about up to a few hundred AMU for positive and thousands of AMU for negative ions. And these molecules are increasing size hydrocarbons and nitrogen containing species which diffuse afterwards downwards. So we have a wide variety of simple but necessary organic species available along with aerosols for continued chemistry in Titan's atmosphere. And this all comes from the first 2 mother molecules that you see on the bottom left, nitrogen and methane. And all of this creates the organic haze that we have on Titan and lands eventually on the surface. The measurements that Cassini made, I just described the INMS, which was a huge breakthrough, were completed by measurements by the Cassini CIRS instrument, which is an infrared spectrometer that operates in the 200 to 1500 wave number spectral region with a spectral resolution of as high as 0.5 wave numbers. It was a remote sensing instrument. It allowed us to measure the temperature, thermal properties, and composition of Titan. And it gave us access to the vertical distribution and the thermal and chemical structure of Titan, which allowed to confirm and to adjust and to correct the photochemical models that existed up to that time. Now, closer to the ground, Cassini-Huygens finally allowed for firm detection of major components by measurements that were performed, for instance, by the Huygens gas chromatograph mass spectrometer, GCMS, which was a chemical analyzer that identified and measured chemicals in Titan's atmosphere. It was equipped with samplers that were filled at high altitude for analysis. And this is how we saw during the descent all the products that came also from an analyzed pyrolysis products from the aerosol collector pyrolyser. So finally, the GCMS gave us the composition of the surface. And like I said before, the lower atmosphere of Titan was a huge unknown before Cassini arrived there. But after Cassini, you can see here, this is a table of all the molecules we knew up to 2008, and we know more now, but you can see this addition of the small table on the right, that these are molecules that we got from the INMS in the upper atmosphere of Titan. And you can see who also derived their abundances from currently existing models. At the time, I also took a look at the spectra that we got from Voyager 1 IRIS compared to the Cassini CIRS measurements. And we have factors of 10 improvement in spectral resolution, which allowed us to absolutely gain a lot in information on the abundances of the different components. And when we compared the CIRS 2010 and the 1980 Voyager 1 IRIS spectra, that is exactly the same season as the Voyager encounter 30 years later, we found that there was a return to the 1980 stratospheric temperatures and abundances, so not much change achieved around the equatorial regions, which is indicative, obviously, that the solar radiation is the dominating source, even at 10 astronomical units, as for the Earth. But we found some small differences concerning some of the more complex hydrocarbons, and there are small interannual variations. But then also from the ground, people shouldn't forget that the ground-based measurements that we make are very complementary to what we have from space missions. And these are measurements from ALMA, the Atacama Large Millimeter Submillimeter Array in Chile. And these are from observations that Martin Gardner made, which show the detections of additional molecules that we have in Titan's atmosphere, and isotopologues actually. And you can see here, for instance, detections of propionitrile, acrylonitrile also, and other anacetonitrile isotopologues that we have in Titan's atmosphere. And all of this was measured from the ground and added a lot to our understanding of photochemical models in Titan's atmosphere. Fabulous discoveries that are actually continued. ALMA is making huge progress in our understanding of Titan, both in terms of composition and also of jets in the upper atmosphere. So there's also meteorology on Titan, and these are observations of Titan's high altitude methane ice clouds on the left that you see, and that we found to be actually ethane ice identified after the observations, very similar to some of the exotic clouds found far above Earth's poles that you see here on the right. There was also indication of a vortex that we found near Titan's south pole, where you see it here. You see also the detached haze along the limb. This is what you see here in green. The polar vortex is what you see in blue, and the insert shows a natural color view, always from Cassini, of the southern polar vortex, which is a huge swirling cloud that was first observed in 2012 and thought to be made of frozen hydrogen cyanide or other nitrile condensates. These are huge systems, but there were also smaller clouds on Titan. And you see some of them here, which is a manifestation, obviously, of the hydrological cycle on Titan, with steady evaporation from the surface that increases the atmospheric moisture until humidity reaches a critical value to allow for cumulus convection when clouds and rain form. There are also observations on Titan of mid-latitude clouds that you see here were captured by the Cassini spacecraft in 2009. After fall, actually, this autumn season began in the southern hemisphere. And these are in the lowest part of the atmosphere. They appear while they appear in white form, what you can see here in the lower part of the image, and they are concentrated between 45 and 63 degrees south latitude. So a lot of interesting things, and again, manifestations of the alkanological cycle on Titan, which is all connected with the dynamics in Titan's atmosphere, the circulation. And you can see here predictions from general circulation models where heat is circulated through Titan's atmosphere via pole-to-pole cycle of warm gases upwelling at the summer pole and cold gases subsiding in the winter pole. So Cassini's observations has shown a large-scale reversal of the system beginning immediately after the equinox in 2009. And so we find that Titan's hemispheres really respond in different ways to these seasonal changes. The seasonal changes are depicted here. The time of the Voyager encounter, Titan's northern hemisphere was coming out of winter. And during the Cassini observations, Titan's northern hemisphere moved from winter to spring, while the opposite is true for the southern hemisphere. So we looked at the evolution in Titan's atmosphere during all of that time, and we witnessed strong enhancements of gaseous constituents and dramatic drop in temperatures, depending on which pole you're looking at. And this was done here, for instance, for the thermal structure with the CIRS instrument on the orbiter. And we see the wintry effects to have led to a drop of about 40 degrees in temperature in the southern polar stratosphere over the last 4 years or so, within 4 years. So this contrasts with a more gradual warming in the northern hemisphere. But at the end of the mission, we found that the North Polar region is beginning to show a reaction to the increasing sunlight, and the temperatures are slowly increasing. But mainly this dramatic drop in temperature was observed by Cassini, and it was connected to a strong enhancement of trace gases in Titan's atmosphere in the South Pole, where the data show that the molecules actually started getting enhanced at some point, but between late 2014 and early 2017, they started also decreasing very rapidly, actually. And so these corresponds with the results that we have in the thermal structure, and it's tied to the seasonal effects and circulation on Titan, demonstrating that between vernal equinox and summer solstice, the circulation pattern changes from a two-shell circulation with upwelling at the equator and descending at the poles to one global shell circulation ascending from the summer pole and descending to the winter pole. So this transition period, it's about 3 terrestrial years. And you can see here how these variations were very important between 2012 and 2018, with blue is the southern polar region, with these components increasing very rapidly. And in red, you have the North Polar region, which it's compensating by the decrease in the amounts of the constituents we have in the atmosphere. So turning to the surface, everybody knows how exciting were the discoveries on Titan's surface by Cassini-Huygens. There were a lot of discoveries made by the Cassini radar, which actually allowed us to go probe underneath the haze. And we saw a number of interesting things on Titan, mainly some craters, not very many of those, but you can see one in the upper left corner here. You had the dunes, longitudinal dunes that were created from very small particles, ice particles on Titan. And also, of course, the question was of the missing methane and ethane. And here you see Jonathan Lunin, who had predicted there would be a lot of liquid hydrocarbons on Titan's surface. And in the beginning, we thought there was none. But after a while, we discovered the rivers and the lakes in the North Polar region, which could actually contribute to the missing methane reservoir. And there were a lot of observations, recent observations of these lakes because of the very close encounter with Titan in 2017. And the Cassini spacecraft used its radar at that very last encounter as a sounder to probe the depth of several lakes. This was the first time that Titan's lakes, as opposed to the seas, have been viewed in sounding configuration. And it has been shown that these lakes can exceed 100 meters depth, and their transparency indicates that they have a methane dominated composition. This composition differs significantly from at the Pole Lakes than for the Ontario Lacus, which is the only major lake in Titan's southern hemisphere, which is more Ethane rich. And this is interpreted as topography of Titan's lakes as the effect of karstic dissolution processes acting on the surface, although the nature of the raised rims remains unknown. And in the methane-rich North Polar lakes, they are perched hundreds of meters above the major seas. They're formed, like I said, by a karstic type process, and then they drain by subsurface flow at quite significant rates. And the subsurface reservoirs and flows therefore may be an important element of the Titan geochemical system. Furthermore, it was very recently shown using radar data that steep-rimmed lakes are creating from nitrogen explosions. The warming nitrogen actually underneath the surface could create basins in Titan's crust. And also we have been able to combine VIMS and radar images of 3 small Titan lakes that show liquid in small lakes inlet in the northern winter. This was in 2006. But recently, a combination of the data showed dry lake surfaces. So there are seasonal changes on Titan also that we can observe also in some of the little systems of lakes that we have there. And the lakes are very important as Francois Roland pointed out in 2008. Titan is the only other place besides the Earth to possess this liquid exposed on the surface, and there are strong interactions between that and the atmosphere. Something that was very much compounded by the Huygens probe, which actually was released by the Cassini spacecraft on Christmas Day, December 25th, 2004, by means of a spring and spiral rails intended to rotate actually the probe for greater stability. And it entered the atmosphere of Titan with 3 parachutes, landed on January 14, 2005. And after a 2.5-hour descent, landed on solid ground. So it returned data to the Earth for around 90 minutes using the orbiter as a relay. But more than that, we got from ground-based observatories that recovered actually data for almost 3 hours from the surface. And here you have a picture of the DISR team at ASI in Darmstadt, Germany on the 14th of January 2005. And let me tell you, we're all very perplexed, as you can see here, because there were some issues with the probe. One of them had to do with the fact that it was discovered actually right after Cassini's launch, that the data sent back from the probe to ESA was unreadable because the engineers had failed to allow for the doppler shift between the lander and the mother craft. And so the Cassini receiver wouldn't be able to receive the data from the Huygens during its descent, but a workaround solution was found to recover the mission. The trajectory of Cassini was altered to reduce the relative velocity, and so we recovered the data. Mostly because there was indeed also a software error in the transmittance of channel A, because actually the relay was done using two redundant S-band radio systems referred to as channel A and channel B. And channel A was the sole path actually to, channel A was the sole path for an experiment to measure wind speeds by studying tiny frequency changes caused by Huygens motion. And so because channel A of a software design error where the receiver on the orbiter was never commanded to turn it on, it wasn't used, and only 350 pictures were received instead of the 700 planned. And all Doppler radio measurements between Cassini and Huygens were lost as well. But mainly some of the measurements were recovered thanks to the fact that Titan's very weak signal was captured by Earth-based radio telescopes. And also there was some worry with the rotation of the probe. And let me tell you, for us who were there in Darmstadt, it took quite some time to figure out how to put together the panoramas we were getting from actually the probe and from the DISR instrument. But in the end, we managed, and we got the data, and we got the fabulous images, and most of all, we got the measurements that were very important. In particular from the ASI instrument, which in addition to the main structure found by Voyager, showed that they recorded several temperature fluctuations due to dynamical, that is gravity and tidal phenomena at higher levels in the atmosphere, where we have gravity waves, and measured with precision the temperature and the pressure at the surface. And the DISR fabulous images, this is a mosaic showing the channels. It's from an altitude of about 7 kilometers. And you see the channels and the rivers that flow into the middle where there is a dry lake. And this is the images that we got from the surface that show the pebbles strewn on a bed of a riverbed, probably made of methane, but was dry at the time, but was shown to have been evaporating later on. This is a general view of what you saw from an altitude of 10 kilometers with the different ridges and the plains. And all of these beautiful images show how important it is to understand the processes that shape Titan. And in that, you have to get information from all different scales. For instance, you need the large scale networks and topography for fluvial processes, mid-scale observations to understand runoff threshold, for instance, and floor fill, and small scale to characterize the sediment itself. The DISR measurements remain somewhat a mystery today because we haven't been able to reproduce completely the reflectivity that was recorded by DISR. It cannot be reproduced by mixtures of ice and organics that we have today in laboratory, but we did get the methane abundance profile, and that was also thanks to the fact that we could switch on a lamp to illuminate the surface. And that from that we got the reflectance that I showed before, and also the information on the lower parts of the atmosphere, where we discovered a whole host of molecules that exist there with ethane, acetylene, cyanogen, benzene, and in addition, carbon dioxide that you can see on this spectrum of the GCMS, which data were published in 2005 and 2010. Wonderful results also showing methane evaporating from the surface after warming from the heated sample inlet. So I just wanted to advertise here, because we're talking about the Huygens probe, that there are new products derived from Huygens observations, and they're available in the ESA Science Archive guest storage facility. Nicola Altobelli has sent me this information, and you have here the links from which you can retrieve all of these products. And there was also a paper published recently by Doton et al. So please think of using this data. Very important information of combined measurements by the Huygens probe, but also from Saturn Orbit. You can see here that these observations from different instruments have revealed the surface of Titan as completely as we can, although we haven't observed the whole surface of Titan, but we saw these dune fields, the lakes, mountainous terrain. We have the dendritic erosion patterns and erosional remnants, and all of this indicate dynamic surface processes that are very much in contact with the atmosphere, where we have meteorology and climate change. And it's an active working fluid that we have in methane on Titan. And the cycle we're observing is active but different from the one on the Earth, because Titan lacks a surface methane ocean, basically. But we're beginning to better understand this world today with its alkanological cycle. And you can see here this depiction by the paper, from a paper by Alexander Hayes et al., where we have all these kind of different processes taking place at different times. I recommend that you look at it, because Alex has done a great job in assembling all this information together on how Titan works. I wouldn't like to get away from this without saying that Titan has been demonstrating to be also alive in the inside, where we have a strong indication of the presence of a liquid water ocean somewhere, sandwiched between two ice layers, as you can see up here on the right hand, with a model by Toby et al. And different indications like the spin rate, but also observations from Huygens, who measured radio waves at extremely low frequency. All of these indications and gravity measurements from Yes et al. Come together to show that Titan's internal structure does have room for this liquid water ocean, as I was saying. And in this image, what is really touching is this drawing by Carl Sagan, which, if you look closely, the third layer says H2O, NH3 liquid layers. So, so Carl had actually, in this depiction, made a very accurate prediction of what Titan's interior would be like a long time before actually we got the information from Cassini. So Titan is an astrobiological object, possibly a habitable world. It has certainly all the requirements that we need for habitable worlds, with the physical conditions, the organic chemistry, the undersurface water, ocean, the climate, a stable environment. And Titan and Enceladus together are certainly very rich worlds in terms of their uniqueness, but also in what they tell us about the Earth. All of the aspects of the Earth, for the climate, the organic chemistry, possibly the emergence of life, are there, sitting there in the Saturnian system. And the discoveries happened thanks to this wonderful Cassini-Huygens mission, which actually had a very fitting grand finale ending with the amazing ring-crossing orbits in the end, that started sometime in April 2017 and ended in September with the impact orbit, where the Cassini mission went into the planet, but not before having delivered some amazing information on the ring structure when they went actually through the rings. In Cassini's final days, we got a lot of information for the planet, for the icy moons and the rings, and also for Titan. And most importantly, also, we got a direct sampling of Saturn's atmosphere, where we went and crashed. And so this mission is really an amazing one. And I had the pleasure, or rather the sadness, of living its final moments in September 2017. We're here at JPL looking at the signal from the mission that went down and down. And we were very sad to lose this mission, but certainly the results from this mission are going to provide information for 3 generations of astronomers to come and data for them to analyze. The numbers behind this mission are absolutely fabulous, not to mention the 5,000 people that worked there. So in ending, I just wanted to say that the Cassini mission has offered us the opportunity to answer a lot of questions that we had on Titan before it got there. Some of these questions were detailed in a paper by Nixon et al., and he called it cold cases. We managed to answer some of the questions on the hydrocarbon oceans, the spectral refraction. What the Huygens probe told us about the ground was absolutely fantastic in the context of the Cassini orbiter. But there are many questions unanswered, and they have to do again with the atmosphere, what we have in there, the surface, the hydrogen gradient, the methane that we find, and the seasons, because we've only observed 2 of the seasons on Titan. So obviously we would like very much to go back, in particular because moons like Titan offer us the perfect atmosphere to go inside and perform observations, because it is so dense that we can actually fly balloons and airplanes in there. But very importantly, we do have a new mission now that was selected in the New Frontiers 4 call of NASA. That's the Dragonfly mission. It's so modern, fashionable. This is a drone that goes there and explores the surface, hopping from one place to the other to get different sites of interest on the surface, and to study all kinds of different aspects, including surface composition in different geologic settings, the dense atmosphere in the lower part, sample materials, characterize the habitability of Titan's environment, investigate possibly how far the prebiotic chemistry has progressed, and even to search for chemical signatures that would be indicative of water-based and or hydrocarbon-based life. The launch is in 2026 and the landing is foreseen in 2034. And ZB Turtle is the PI, and they're doing a fantastic job there. So Titan, like Europa, Ganymede, and other worlds, are the ocean worlds in the solar system, and they have a lot of water, where we thought that Earth was the planet that had the most water in the solar system. This is not the case. These bodies may contain up to 10 times more water underneath their surfaces. So it's very important to explore them. And I don't know if we'll have another Cassini mission in the future like this one, but we are very thankful. The lesson learned here is always plan for the worst, but be ready for the best. I've heard that before. A scenario-based science planning might have exploited better the impact survival, but we got so much data from this mission that we hadn't foreseen or planned for before. This is a fantastic mission. It will provide data to be analyzed both in science and in engineering and in outreach for many decades to come. So thank you, Cassini-Huygens, and thank you all for your attention.
Thank you, Athena. Thank you very much for this very fascinating talk. I'll see that I can get your video back on.
I'm trying. Let's see.
Okay. We're running a little late, but anyway, I mean, Athena agreed that she would stay on for a little longer and answer questions. And as we did in the last times, I mean, we have 2 possibilities. You can either write your questions in the chat channel and I will read it to Athena, or you raise your hand and then Saliba will give the microphone basically to you, and you can ask your question yourself. So I'm looking at the chat channel, and here I have the first question is, what's the current thinking about signs of life on Titan? I'm thinking in particular about the origin of the methane. On Earth, methane is emitted by bacteria. Okay, Athena, that's a good question for you.
Yes, there have been actually investigations and theories and suggestions about possible living forms on Titan, in particular by Chris McKay and his team, who advocated the presence perhaps of something like methanogens on Titan's surface that would actually feed on hydrogen, if I remember correctly. The amounts that we find, the isotope measurements that we've made, do not indicate any biological, they're not compatible with biological origin of the methane on Titan. But one never knows, and there have been, this is a study in progress, these investigations are in progress and thinking all the way up to membranes on Titan and whatnot. So this is my current knowledge.
I had a follow-up question. I mean, life must be very slow there at those
and very different, no? Probably. Yes, very different, I would also say. The chemical reactions are so slow and there's so little light. So I don't know exactly how they survive. But look on Earth. I mean, you have all these extremophiles.
Okay. So Andrew Accardio is asking, thank you for the talk first, but the question is, was the Huygens probe designed to float if it happened to land on a liquid Ethane lake, or would it have immediately sunk?
It wasn't designed to float or to land. If we had gone down that path, as many people connected here today know, we would have had to change a lot of things on the probe, made it more landing compatible, if I can say. If it had landed on a liquid, it would have depended, I should think, on the depth of the liquid extent it would go in, and it might have floating. I don't think it was a very heavy probe, but it wasn't designed. It was designed as a descent probe, and it became a lander out of sheer luck. We were all very happy.
Yeah, yeah. So the Evelyn Larson is asking, can you speak a little bit about what we know about the composition of the silicate core? I would think there's an iron core, but
I'm sorry.
The question is yours. The composition of the silicate core.
Oh.
Titan.
Oh, it's, you know, I don't know very much about the silicate core, but Titan is expected to have something very similar to the Earth's, I would think, right?
I would think there's a silicate rock layer, and underneath probably a iron-rich core. I would think. Yeah.
Yeah.
Anyways, wonderful update. Leo Enright says, can you give a citation for the Sagan note? Where might I find it? That was a question I had too.
What? You had two, Dilman?
Yeah, where can you find that
I'll find out the reference and communicate it to you. I was actually talking a lot with Carl until he passed, because he was a Titanophile and very, very interested on Titan. And I think I have some of his notes and scribblings, but I think this was published somewhere. I'll try to find it and get you the reference.
Okay, I see we have two raised hands, you know, and Saliba, for a change, would you give the floor to
the
first one of them?
In the meantime, there's a question about lakes changing with season, and yes, they are. I showed a picture of how the lakes changed over a period of about 6 years, and we see them shrinking and changing their shape. So they do change with time. Yes, I answered one of the chat questions.
Yeah, I see that one. Yeah, and there was one before: slow life on Titan, but fast living on Enceladus. Rommel. How do you know?
Yes, John. Yes, maybe. Yes, it could be. Titan and Enceladus have similarities in the habitability conditions, but I should think they're very different one from the other. So maybe yes, slow and fast.
Okay, Saliba, give
Okay.
the floor to the first.
Sure. The first one is Professor Bonnet. Could you please unmute your microphone?
Hello, Roger.
Okay, can you hear me?
Yes.
Thank you very much, Athena. It was a wonderful, wonderful correspondence, and I really appreciated it. I just wanted to mention two small points of history. We are in ASI here in Switzerland. So the first point is that you may not know, but that the name of Huygens was a result of a confrontation between the delegate of Switzerland at the Council of ASI, who complained that what would become the Huygens probe was called the European probe. And he complained about that, and he said we should find another more sexy name. So I was sitting around the table of the council, and I just read a lot of things about Huygens. So I said, Titan, Huygens.
Yes.
Of course, the Dutch delegate was absolutely happy with this, and it became the Huygens probe. The second one, talking about habitants on the surface of Titan, I cannot resist to remind you that on the probe, there is a DVD, a CD plutôt, which records several messages, a large number of messages, among which you find Uber Reeves, but also my daughter and my nephew, and they were asked to record what this mission inspired them in view of possible inhabitants of Titan, or people who would visit Titan one day, could analyze and think about what was the mood of the people in the end of the century. So this is still there. If you go to Titan, do not forget to look at the probe, okay?
I would love to go to Titan, Roger. It's my next trip whenever we get out of lockdown.
I go with you.
Thank you. Thank you. I see a brief question, was lightning ever discovered? And I can answer that so far, no, not on Titan. We haven't discovered lightning. We've looked for it. I actually did look for it at some point. Not in an obvious way, no.
John Zanecki has raised his hand.
Yeah. John, could you please unmute your microphone?
Hi there, Athena. Can you hear me?
Hi, John. Yes,
Hi.
we can hear you.
Thank you for a great talk. It was fantastic. You managed to pack in a lot into an hour. One question and one comment, if I may. First of all, the question. All those surface features you described, they had, from my memory, they had been considered before we arrived, except for the dunes. And the dunes are surprising, are they not? Because the winds, as far as we know, are very, very light, generally, on Titan. And to produce dunes, you need, apart from particulates, you need winds, don't you? So
yes.
Has there been much thought about that? That's the question. And the comment, I just feel I have to speak up in defense of the Huygens engineers, who you accused of not allowing for the Doppler effect, which I think is not fair. They did know about the Doppler effect. I think that the problem is a very, very subtle one, and there was an investigation into that issue. But I just feel I had to make that comment that they hadn't just forgotten the Doppler effect.
Yeah, I was probably brief on that, John, and a bit schematic. Thank you. I'm sure they knew about the Doppler effect, and this mission is a huge engineering achievement. I mean, my God, if we go on that trip with Roger, I would very much like to be on a mission that is put together by the same engineers. I mean, or their know-how. So yes, and it was really being very brief and schematizing about the Doppler effect. But there was an issue and it was resolved. And the main point here was to show that all the problems that came on board were resolved one way or the other. and made this this mission a success. Indeed, many of the features we thought about before that we saw at Cassini, although we thought there would be more craters, as I recall, and we didn't find that many. The lakes in the north, and all in the north and not everywhere. I don't know that everybody had thought of that. But I showed this schematic from Jonathan in 1990, and he showed most of the things that we discovered afterwards, indeed. The dunes, I think, there have been a lot of investigations on the dunes, how you could form them in this longitudinal shape that, like you said, on Earth is created by winds on Titan. And the answer is the particles that you have on Titan's surface that form these dunes are very light, icy, mainly particles that are very light. They have some organic components in there. And you can form them because actually you do have a little bit of wind on Titan's surface. And apparently it's enough to move these tiny little light particles around and create the dunes that we see today. But this investigation is ongoing, and indeed it's one of the most interesting and compelling aspects we see on Titan.
So I'll go back to the chat channel. There's a question by Georg Fischer. Are the lakes changing with season? Is it known by how much? Could they completely disappear?
Yeah, like I said before, yes, I showed that they do change with season. They shrink. We've seen that over a period of years. In the current season, we saw them essentially shrinking in the north. We don't know if they completely disappear because there are different processes, both on Titan's surface and in Titan's atmosphere taking place, that cover more than the two seasons that we've witnessed so far. Could they entirely disappear? They might. We don't know enough right now, but we keep we monitored them over 13 years, and we saw them changing both in shape and in content.
Okay, Denton Evil has two questions. First, Titan is very reduced, yes. Then more likely Mercury with a lot of silicon dissolved in the iron-rich core as metal. Matter of pressure too, but.
Yeah. Yes, and not the same atmosphere, I would say. So you can compare Titan to a lot of different things. I don't compare it to anything. I think Titan is quite unique. You can find aspects of it on different solar system objects, but in my mind, it's quite unique.
And he has another question, just the next one, not enough mesoscale convection for lightning, question mark.
Possibly, yes.
Then Georg Fischer has a suggestion for a paper on lightning. I think we can skip that. Can a good case be made for sending Dragonfly to the Huygens site, or are there much more valuable targets by Liam Enright? Irish TV.
That's a good question. So Dragonfly is going to it's first seen to land more in mid-latitude near the equator, actually. Now, whether it should land on the same site as Huygens, I could see scientific arguments for that. Yes, we could go back and see what is the current methane evaporation rate, for instance. Do we have more indication of liquid? Is anything changing in this dry lake where we landed with Huygens? And take samples that would help now that we have the context there. At the same time, we do want to explore other places, and this is the beauty of Dragonfly, because it can hop several meters away from one side to the next, and I think that's very important. So yes, both its features, I think, are very, very good.
Go back to the raised hand. So Hans Sinneke has raised his hand. So Lieber, give the floor to him.
Yeah, could you please unmute your microphone, Hans?
Okay, can you hear me?
Yes.
Yes.
Okay, well, thank you so much for this fascinating talk. My question is, you mentioned the engineering, and before the engineering, you have to figure out how to get there with the flybys. And my immediate question was, what is the margin of error to get there? Because it's a small error and then they accumulate.
Hans, you have a feedback.
Yeah, so if that is what is the margin of error, oh, somebody has Can you hear me? Yeah. Yeah. It's too much.
Hamza, I guess you have to mute your microphone because we'll have a feedback. Okay, Athena, try again.
Yeah, I was saying, I don't know the answer to exactly what is the margin of error. That's a very engineering question. Perhaps Jean-Pierre would know the answer to that. What I do know is that indeed the trajectory was very, very carefully calculated. What amazed me was when we got there and we went through the rings and we came out unscathed, because that was the most terrifying moments that I recall when we were watching the spacecraft going in and out through the rings, and we were thinking, oh my God, you know, something is going to hit the instruments and we won't be able to make our measurements. So I don't know the margin error, but I know that the engineers had done a great job in the trajectory and calculating how to go through the main divisions of the rings without, you know, putting the spacecraft in danger and the instruments.
Okay, Athena, you told me that you had time until 20 past the hour, if I'm not mistaken, but we have one more. John Rummel has a question, and maybe we can take that one and then we'll close the, or do we have more time?
Sure, no, sure. And John may have more ideas about Titan and life and so on, but John, please.
Could you unmute your microphone, please?
No, I'm just curious as to whether or not some of the same processes that dominate Titan, especially the subsurface, are also going on in Enceladus. And I think it's well worth a mission to go back and find out.
Oh, thank you so much. Absolutely. And although I think the subsurface is a little bit different between the liquid content, and the subsurface of Titan and Enceladus is probably different in terms of distribution. Enceladus is probably in direct, Enceladus ocean is probably in direct contact with the silicate core, actually, much as on Earth. And on Titan, we don't think that is the case because we have the two ice layers above and beneath. But still, it's two categories of habitable worlds that we really need to investigate more. Europa and Ganymede are the similar bodies in the Jupiter system that we also need to go back and to go and explore. And we have missions there that are planned. But definitely for Titan and Enceladus, my hope, and if I can end with that, is that any future mission going out all the way out to the Saturnian system could please be another amazing international collaboration like the one we had for Cassini-Huygens. And if that happens, then I'm sure we'll have the best possible mission and a worthy heir to the Cassini mission.
What a nice final word. Thank you very, very much indeed. And I would like to thank you, in behalf of ISI and behalf of the audience. We had 150 people participating today. Thank you very much. And, for all the participants still remaining here, let me just announce you that next week we have Jessica Agarwal speak on Rosetta. And with that, have a good day, good evening, good morning, wherever you are. Thank you very much, Athena.
Keep safe. Thank you.
Bye-bye.
Thank you. Bye.